All right, so the final lesson, lesson 10.8 of final lesson of chapter 10, we're going to deal with scale drawings and scale models. So we're using those ratios and proportions, but in this case, we're going to find the lengths of, say, distances through a park using maps, using scale models, and so on. So let's go ahead and jump right in. Scale drawing, first of all, is a two-dimensional drawing of an object that is proportional to the object, okay? So for example, a map or a blueprint, okay? Obviously, it's sort of hard to draw a Michigan-sized, well, we don't have a Michigan-sized piece of paper to put the actual drawing of Michigan on. So we have to take Michigan, the state, and shrink it down to paper size so that we can actually use it and so on. Same thing with a blueprint. A blueprint is the designs usually for a house or a building of some sort. Well, we don't have paper big enough to make a full-size drawing usually of the house, so we have to scale it down so that we can actually use them. So we're taking a drawing of a large object and putting it on paper to use. So to do that, we have to have a scale, and the scale is a ratio, so it's a fraction of the dimensions in the drawing to the dimensions of the object. So here are some examples. We might have a 1 to 20 scale, which tells us that 1 unit on the drawing is 20 units in reality. Okay, so if we have an inch here, that may be 20 inches in real life, or 1 centimeter to 1 meter. So 1 centimeter on the paper represents 1 full meter on the drawing, or a 1/4 inch equals 1 foot. So a 1/4 inch on the drawing is equal to 1 foot in reality. Okay. So first we're going to use proportions to find an unknown scale. All right, so the length of an object on a scale drawing is 8 centimeters, and its actual length is 48 meters. The scale then is 1 centimeter to what? All right, now one of the things, and we can do this numerous ways. All right, so 8 centimeters on the drawing is 48 meters. All right, so that is equal to 1 centimeter to some meters. Now we have choices in this particular case. One, I hope you realize that if we were to just simply divide by 8, 8 divided by 8 is 1, 48 divided by 8 is, okay, and we could fill in the blanks and so on. Or we do have our, let's say, I'll just use X. We could do our cross products. Okay, so my point in this particular case is you do have your options of how to deal with this particular issue. So however you want to do it. In some cases it might be simple. In other cases it might be a little bit more complex. You might have to do a little bit more work. But obviously 48, in this case 48 divided by 8 is 6. So it may be relatively. So in this particular case though, 1 centimeter on the drawing represents 6 meters in real life. And again, these are things that we do a lot of times on maps and in blueprints. So, all right, so here we're going to have a map to use. So on a map, the distance between Smith's shelter and Hunt's hideout is about 1.75 inches. What is the actual distance? Okay, so from Smith's shelter, and again, you have your map here. You see the blue line here represents a river. These black lines are trails. There's a bridge over the river. But the distance represented or on the map here from Smith's shelter to Hunt's hideout is approximately 1.795 inches. We want to know the actual distance in reality. Now you'll notice down here at the bottom we are provided a scale, and we are told that in this particular case 1/4 inch, which I'm going to go ahead because up here we're dealing in decimals. I'm going to go 0.25, so 1/4 inch is equal to 2 miles in reality. Okay, so this, what you're talking about is like maybe some national park or something where you're hiking or so on, and you want to know the distance between objects and on the trails. Okay, so now we want to know what is the actual distance between the two. Well, somebody took a ruler and measured between the two and found that on the map we have 1.75 inches between the two landmarks. Okay, our job is what is the actual distance. And I'm going to use d in this case for distance. All right, so we have a number of ways that we can do this. But I'm going to go ahead. We've been working with our cross products. I'm going to go ahead and just use cross products. So 0.25 times d is 0.25d. Actually, I guess I'm used to using small case letters when I work with equations. So that's why it's no big deal that I translated it, but I did just because that's what I usually do. And 1.75 times 2 will end up being 3.5. All right, so now we have our equation, and we solve our equation. In this case, we're going to divide both by 0.25. All right, and so 3.5 divided by 0.25 is 14, and this would then be miles. So again, we're talking in this case by some large park if these two things are 14 miles apart. Again, maybe you're hiking. Maybe it's the Appalachian Trail, the various places around our country where we have big parks and big hiking, places and so on. All right, then we get into scale models. The scale model is a three-dimensional model that accurately represents a solid object. So anybody who's into model planes, model cars, model trucks, anybody, usually architects, a lot of times they will, before they build a building, a big building, they will, they'll do it out on paper, so they'll have their drawing, their scale drawing, and then they'll take it and they'll make a three-dimensional model. Now with computers and so on, we can do a lot of this three-dimensional modeling in a computer. So you get the look of the building just in a smaller version. So a model of a 36-foot tall house was made by using the scale 3 inches to 2 feet. What is the height of the model? So we know in any case that 3 inches, and I'm going to go ahead and write my scale, is 2 feet. Now if you went 2 feet over 3 inches, that would actually be the same, okay? So now we know that the model of a 36-foot tall house, so 36 foot, and this is going to go down here, because we're talking down here, we're talking about the height or the sizes of the actual object. Up here, we're talking about the sizes of the model, and we are trying to find. I'll just use X. You could use H or whatever. H would be, or M would be two other good choices for variables in this case, but 2x, cross products here, so 2 times x is 2x. And then 36 times 2, well, let's see, 3 times 6 is 18, carry a 1. 3 times 3, 9, 1 is 10. And then if we divide both by 2, x equals, what, 54 inches. Okay, so in this particular case, the scale model's height is 54 inches tall. So this is a big model if it's 54 inches tall. I mean, 54 divided by 12 is, that's 4.5 feet tall. So the model in this case is 4.5 feet tall. So this is a big model. All right, let's apply a little bit more. A DNA model was built using a scale of 2 centimeters. Now this one might be a little ugly. Over, wow, point, let's see how many zeros. 1, 2, 3, 4, 5, 6, and then 1. 1, 2, 3, 4, 5, 6, and then my 1 millimeters. We got tenths, hundredths, thousands, 10,000s, 100,000, millions, 10 millionths. So 1 10-millionth of a millimeter. Okay. If the model of the DNA chain is, and in this particular case, our model is actually bigger than our DNA. Okay, so usually we're used to models being smaller, but if you really think about it, DNA is part of your genes and so on. And so to actually, I mean, to sort of look at what DNA is, in this case, the model is bigger. Okay, so equals a DNA chain that is 17 centimeters long. So this, in this case, the model is bigger. And we want to know what is the length of the actual chain. I will use C for chain, just because. Okay? So let's see. Let's go ahead and multiply 2 times c. That's 2c, right? And then 17 times, we said, let's see, well, that was 10 millions, right? Tens, hundreds, thousands, 10,000s, 100,000 million. Yeah, 10 millions. Or 17 times our 10 millions is 0.1, 2, it's going to be 3, 4, 5, 1, and then 1, 7. Yep, that's, yep. There we go. All right, so tens, hundreds, thousands, 10,000s, millions, 10 million, 100 millions. Gosh, this gets uglier and uglier. Okay, but anyway, so that's our cross products the other way. And then if we divide by 2, c equals, let's divide by 2. That's going to be, oh gosh, 0.00 and 0, 0, 0, 0, and then 8, 5. Yeah, that's sort of an ugly one. Millimeters. So, again, the actual length of DNA, again, it's not something we could actually hold in our hands and so on. So this is just tiny, microscopic in a way. So we have to have the model in order to see it and actually sort of get an idea of what it is, how it's structured, what it looks like, and so on. But yeah, absolutely tiny is the size of the DNA strand. So, all right, off to do some applications. Good luck.